स्वागत है दोस्तों एसआर एकेडमी 2.0 में। आज हम कॉम्पिटिटिव एग्जाम्स के लिए ऑप्टिक्स को बिल्कुल डिकोड करेंगे। कभी सोचा है नासा के विशाल स्पेस टेलीस्कोप लेंस के बजाय सिर्फ और सिर्फ दर्पणों पर क्यों टिके हैं? दरअसल दर्पण अंतरिक्ष के लिए हल्के होते हैं, पॉलिश करने में आसान है और प्रकाश को सोखते भी नहीं। बेसिक समझें। अवतल दर्पण प्रकाश को एक बिंदु पर सिकोड़ते हैं, जबकि उत्तल दर्पण उसे बाहर की तरफ फैलाते हैं। किरण आरेखों को ध्यान से देखिए। समानांतर किरणों का कटना ही तय करता है कि इमेज आखिर बनेगी कहां। ये साइन कन्वेंशन टेबल एक ब्रह्मास्त्र है। न्यूमेरिकल सॉल्व करने के लिए इसे तुरंत याद कर लीजिए। दर्पण सूत्र और आवर्धन के फॉर्मूले एग्जाम्स में आपके सबसे बड़े हथियार हैं। इन्हें एकदम रट डालिए। अब लेंस की बात करें तो पतले लेंस की फोकस दूरी इस मशहूर लेंस मेकर इक्वेशन से तय होती है।
एक गजब की ट्रिक बताऊं? उत्तल लेंस प्रकाश को बिल्कुल अवतल दर्पण की तरह ही एक जगह मिलाता है।
असल जिंदगी में डेंटिस्ट और गाड़ियों की हेडलाइट्स लाइट को फोकस करने के लिए अवतल दर्पण ही इस्तेमाल करते हैं। वहीं दूसरी ओर गाड़ियों के रियर व्यू और एटीएम सिक्योरिटी में उत्तल दर्पण काम आते हैं, जो बड़ा व्यू देते हैं। देखिए, दर्पण से ऑब्जेक्ट की दूरी बदलते ही उसका बनने वाला प्रतिबिंब कैसे एकदम से बदल जाता है। तो चलिए, अब बारी है बीपीएससी और पीजीटी जैसी परीक्षाओं के लिए एक सुपरफास्ट रैपिड फायर रिवीजन की। पहला सवाल, अगर इमेज 10 सेंटीमीटर और ऑब्जेक्ट 2 सेंटीमीटर का है तो इसका मैग्निफिकेशन यानी आवर्धन क्या होगा? बहुत ही सिंपल। इमेज की ऊंचाई को ऑब्जेक्ट से डिवाइड कर दीजिए, सीधा जवाब मिलेगा 5। अगला सवाल, 90 सेंटीमीटर त्रिज्या वाले उत्तल दर्पण से 15 सेंटीमीटर दूर रखी वस्तु की इमेज कहां बनेगी? फॉर्मूले में वैल्यूज रखने से पहले साइन कन्वेंशन लगाना बिल्कुल मत भूलना, यही सबसे अहम कदम है। सही सॉल्व करने पर जवाब मिलेगा पॉजिटिव 11.25 सेंटीमीटर, यानी उत्तल दर्पण के ठीक पीछे एक आभासी इमेज। आखिरी सवाल, अगर उत्तल दर्पण की फोकस दूरी 12.5 सेंटीमीटर है तो उसके वक्रता केंद्र की दूरी क्या होगी? एकदम आसान, त्रिज्या फोकस दूरी की डबल होती है, इसलिए 2 से गुणा करने पर मिलेगा 25 सेंटीमीटर। फिजिक्स में रटने से नहीं, कॉन्सेप्ट समझने से बात बनती है। इन फॉर्मूलों की प्रैक्टिस ही आपकी सफलता पक्की करेगी। सोचिए, क्या हमारी आंखें भी एक कमाल का गोलीय लेंस है? एसआर एकेडमी 2.0 को लाइक, शेयर और सब्सक्राइब करें।
When you drive a car at night, you rely on two curved mirrors performing exact opposite tasks. The headlights use a curved surface to blast a narrow beam of light far down the road, while the side view mirror curves outward to squeeze multiple lanes of traffic into a piece of glass the size of your hand. Mastering these opposing behaviors and solving competitive exam questions requires two mathematical tools. These formulas relate 3 physical distances. First, the distance from the mirror to the object, u. Second, the image distance, v. And third, the mirror's focal length, f. Memorizing the letters won't help you solve an actual problem. The math only works if you can correctly identify which of these distances are positive or negative in physical space. This animated coordinate graph shows how we map standard x and y axes directly onto the mirror. The mirror's center, or pole, locks onto the origin point at 0, 0. Because the source of light, the object, is placed in front of the mirror on the left, the object distance, u, sits on the negative x-axis. It is always a negative value. Let's apply this to a standard convex mirror problem. If an object is placed 15 centimeters away, u is exactly negative 15. A convex mirror has a positive radius of curvature, let's say 90 centimeters, which means the focal length is exactly half of that, positive 45. Plugging these into the mirror formula reveals our final image distance. Orienting the origin point correctly guarantees you will find the right distance. However, calculating the actual size of that reflection introduces a secondary set of rules. If a 2-centimeter object produces a 10-centimeter image, the math gives us a raw magnification factor of 5, but that number alone is incomplete. A positive 5 means the image sits above the x-axis. It is upright and virtual. A negative 5 means the image has dropped below the x-axis. It is inverted and therefore real. Test your intuition. Find the image distance for a real image that is 4 times larger than an object placed 12 centimeters away. The designation of a real image dictates that it is inverted, which fixes the magnification at exactly -4. With u at -12, the final distance v resolves to -48 centimeters. When a dentist needs to see extreme detail, placing an object inside the focal point of a concave mirror produces a positive magnification, creating a virtual, upright, and enlarged reflection. This ray diagram illustrates the geometry of convex mirrors. By extrapolating the reflected rays backward, the mirror compresses a wide field of view into a diminished, virtual image behind the glass, exactly what a driver needs to monitor traffic. This technical diagram shows how reversing the light path changes the physical outcome. A concave mirror takes a single, intense point of light placed exactly at its focus and reflects it outward as a massive parallel beam. Engineers scale this exact geometry up to industrial levels. Massive arrays of parabolic mirrors catch parallel solar rays and bounce them back to a single focal point, generating enough heat to melt metal. These equations dictate the physical behavior of light, from the microscopic scale of a dentist chair to the massive scale of a solar furnace. Mastering spherical optics gives us the power to bend light to our exact specifications.
To see across the universe, we build massive optical systems to capture light that has traveled for billions of years. But capturing light is only half the problem. You also have to predict exactly where every single photon will go once it hits your instrument. Look at the James Webb Space Telescope. Its massive, segmented gold mirrors are built to a physical tolerance of mere nanometers. Every point on those surfaces obeys a simple physical rule. The angle of incidence equals the angle of reflection. But attempting to manually calculate and trace the physical trajectory of billions of light rays bouncing across multiple curved surfaces is an impossible way to engineer a working telescope. To actually design these systems, optical engineers take complex, three-dimensional light fields and abstract them. The physical mirror flattens into a two-dimensional curve on an XY plane, and beams of light become clean geometric lines interacting on a Cartesian grid. By translating physical light into pure algebra, we derive a universal formula that dictates how light behaves. Understanding this geometric derivation is the prerequisite for building any optical tool, from a simple laser pointer to an orbital observatory. To build this mathematical model, we start with the simplest possible geometry, a perfectly flat reflective plane. This diagram shows the geometry of a flat mirror. We assign the physical location of the item in front of the glass as the object distance, represented by the variable p. The perceived depth of the reflection inside the glass is the image distance, or variable q. On a flat plane, the object height h and the image height h' are exactly equal. The ratio between them, our magnification, is exactly 1. And because the light rays bounce off the surface and do not physically penetrate the glass, the image you see is classified as virtual. The math changes the moment we introduce a curve. A spherical mirror is defined geometrically as a physical slice cut from a theoretical larger sphere. Look at this cross-section of a concave curve. The center of that theoretical larger sphere is the center of curvature, marked as C. Because the mirror is curved, incoming parallel red rays reflect inward and converge at a very specific coordinate, the focal point, F. There is a fixed spatial relationship here along the principal axis. The distance from the mirror to the focal point is the focal length. Geometrically, this length is always exactly half the radius of the full sphere. By curving the glass, we break the simple one-to-one mapping of a flat plane. The image is no longer guaranteed to match the object in size or location, requiring a new set of rules to predict where the light will go. To locate an image without physically building the mirror, we trace 3 principal lines of geometry. First, a ray entering parallel to the axis reflects through the focal point. Second, a ray passing through the focal point reflects parallel to the axis. And third, a ray passing through the center of curvature reflects straight back on itself. We can apply these rules to this diagram of a concave mirror. Here, the blue object is placed further away than the focal point. We draw our 3 principal rays originating from the tip of the arrow, applying our reflection rules to each one. Notice where the reflected rays go. They physically intersect in front of the mirror, forming the inverted yellow image arrow. Because the light rays actually converge at this coordinate in physical space, we classify this as a real image. You could put a piece of paper here and actually see the projection. Now, placing the blue object inside the focal point, we trace the same principal rays. The reflected rays now spread out on the front side, never physically intersecting. Extrapolating these diverging lines backward behind the mirror reveals their intersection, creating a large, upright yellow virtual image, an optical illusion. The physics of the mirror did not change between those two examples. The reality of the image, whether it can burn a hole in a piece of paper or just trick your eye, is dictated entirely by where the object sits relative to the mirror's focal point.
Drawing precise ray traces for every single optical setup is tedious and prone to error. The engineering goal is to replace manual drafting with a single algebraic formula that solves for any variable automatically. We derive this formula directly from geometry. In this diagram, focus on the two shaded triangles meeting at vertex V. A light ray strikes the pole and reflects at angle theta. Sharing this reflection angle and bounded by perpendicular heights, the yellow object triangle and blue image triangle form geometrically similar right triangles. Since their proportions are locked, calculating their ratio yields the magnification formula, m equals negative q over p. We insert that negative sign because positive distances here yield an inverted image, requiring a negative height. Next, shift focus to the unshaded triangles, formed by a second ray passing straight through the center of curvature at angle alpha. These are also similar right triangles. We have two sets of triangles sharing the same vertical heights. By setting their geometric ratios equal to each other, we can cross-multiply and isolate the key variables: object distance, image distance, and the mirror's radius. The algebra simplifies down to a remarkably clean intermediate equation: 1 over p plus 1 over q equals 2 over r. We know from our initial rules that the focal length is exactly half of the radius, so we substitute 2 over r with 1 over f to reveal the final unified mirror equation. We have taken the physical behavior of light rays and translated it into pure trigonometry. We now have a predictive mathematical tool that calculates exactly where an image will form for any object distance. But algebra is blind to physical space. The mirror equation will output completely false physical data if we do not constrain those variables within a strict coordinate system. This table shows the Cartesian sign convention. It acts as the compass for our optical math, establishing rigid positive and negative rules for locations in front of the mirror versus in back. The absolute rule is this: any distance measured in front of the mirror's reflective surface is positive. Any distance measured in the dark void behind the mirror is negative. Notice how the focal length flips its sign depending on its physical location. In this convex mirror diagram, the curve bulges outward. Its center of curvature and focal point exist in the negative space behind the glass. Plugging a negative focal length into the mirror equation mathematically guarantees a negative image distance q, locking the image into being virtual, upright, and diminished. Adhering to the sign convention is what allows one single algebraic equation to perfectly predict the behavior of both converging and diverging optical systems. These mathematical outputs directly dictate the physical engineering choices we make when building optical tools. When the equation yields a positive, real, and highly magnified outcome, we know we must manufacture concave surfaces. This geometry is required for instruments needing extreme focus, like solar concentrators melting metal, or orbital telescopes capturing ancient starlight. Conversely, when the math guarantees a virtual, diminished image, we engineer convex curves. That specific geometry compresses a massive field of view into a small space, which is exactly why we use them for vehicle rearview mirrors and ATM security monitors. Up to this point, we have only calculated light bouncing off reflective surfaces, but the true power of this geometry becomes clear when we allow light to pass through a solid medium, like glass. The exact same geometric logic of curvature applies to lenses. The mirror equation naturally evolves into the lensmaker's equation, adding variables for the glass's index of refraction and the radii of its two curved sides.
Predicting the path of the universe's fastest phenomena and engineering the precise tools required to capture it ultimately comes down to understanding the elegant geometry of simple triangles.